Hello everyone. Today I will introduce you to two groundbreaking concepts that have revolutionized the field of artificial intelligence and natural language processing, that is attention mechanism and transformers. These attention mechanisms are fundamentally altered how AI system processes information. Originally, it was introduced to improve the machine translation task where these attention mechanisms allows the models to dynamically focus on the most relevant parts of the input data. This ability mimics the human cognitive process where attention is directed based on the context and relevance. For example, in a language translation task, this attention mechanisms enables the system to selectively weigh the words or phrases that contribute most to the translation accuracy, significantly enhancing the quality of the translation task. Beyond this translation, these attention mechanisms are now integral to tasks such as the text summarization, sentiment analysis, image captioning, and whatever. Wherever this understanding the context is very crucial. So, based on and building on the power of the attention mechanisms, these transformer models were introduced. These transformers were proposed by Vaswani et al. In 2017 and have since become the backbone of many state-of-art AI systems. Previous, we have the models that relied on the sequential processing. Unlike those models, these transformers employs the self-attention mechanisms that allow for simultaneous processing of the entire input sequence. This parallelization not only accelerates the training but also enables the models to capture the long-range dependencies and complex relationships within the data. As a result, these transformers have set the new benchmark for various applications, including the language model, speech recognition, and beyond all. So to grasp the novelty of these transformers, it is crucial first to understand the encoder-decoder framework, attention mechanism, and transfer learning. These foundational concepts are essential for appreciating how transformers have revolutionized the fields like natural language processing. If you see what is the speciality of this encoder-decoder architecture, which replaced the RNN's encoder-decoder architecture forever and now, the way it is dominating the field of computer vision is because it uses attention mechanism. That is what we are going to see now. Before transformers, RNNs in encoder-decoder architecture was used for neural sequence transduction. Prior to transformers, this RNN in LSTMs are the state-of-art in NLP. The feedback loop thus propagates information from one step to another. These architectures were and continue to be widely used for NLP tasks such as the speech processing and time series, etc. One area where these RNNs played an important role was in the development of machine translation systems, where the objective is to map the sequence of words in one language to another. This kind of task is usually tackled with an encoder-decoder or sequence-to-sequence architecture, which is well suited for situations where the input and output both are the sequences of arbitrary length. The job of this encoder is to encode the information from input sequence into the numerical representation that is often called as the last hidden state information. This state is then passed to the decoder, which generates the output sequence. These RNNs are good at learning from sequential data, but there are few limitations. Let's see what are those are. These RNNs are very bad at remembering the long-term dependencies and vulnerable to the vanishing and exploding gradients. So we used a variant of this recurrent neural networks such as LSTM and GRU units with the gated mechanisms which are good at dealing the long-term dependencies, but still it is a challenging task with paragraphs or documents of text as they have more computations. Let's see the encoder-decoder architecture of machine translation task. You can see here both the encoder-decoder blocks of this machine translation task. Here in the encoder, a sequence of RNNs are connected, and the decoder also a sequence of RNNs are connected. The one weakness in this architecture is the final hidden state of the encoder part creates the information bottleneck, because the final hidden state of this encoder block is given to the decoder block. This creates the bottleneck in the information. It has to represent the meaning of the whole input sequence, because this is all the decoder has to access to when generating the output. This is especially challenging for long sequences, where the information at the start of the sequence might be the lost in the process of compressing everything to a single fixed representation. Fortunately, there is a way out of this bottleneck by allowing the decoder have access to all of the encoder hidden states. The general mechanism for this is called the attention, and this is the key component in many model neural network architecture. We can say in the attention mechanism, it has access to all the encoder hidden states information. Although this attention enabled the production much better for translations, there are still major shortcomings with using this recurrent neural models for the encoder and the decoder, because these computations are inherently sequential and cannot be parallelized across the input sequence. With the transformer, a new modeling paradigm was introduced which dispenses with the recurrence altogether and instead rely entirely on a special form of attention that is called self-attention, where the both encoder and decoders have their own self-attention mechanisms whose outputs are feed forward neural networks. This architecture can be trained much faster than recurrent models and paved the way for many of the recent breakthroughs in NLP. Now, coming to the third component which makes you to better understand this transfer learning. Transfer learning is a very crucial component of transformers, and it plays a central role in their success also. So in the transformers, this transfer learning refers to the process of pre-training a model on a large corpus of text and then fine-tuning it on a specific downstream task. If you look at it in a supervised learning stage, training and evaluation will be done on the same task or the domain. You can see here the model A was trained in the domain A for doing the predictions on A. The model B was trained on the domain A and then used for doing the predictions on domain B only. Thus is supervised learning. Coming to the transfer learning, the model which is having the two parts, body A and head A, which is trained on the domain A and used for doing the predictions on domain A, is then used with the domain B. The model was used to initialize the body part was used with a model which is training on another domain B. You can see here the second model is having the two parts, head B but body A. It initialized the body part of A of the previous model, which is already been trained in the domain A for doing the predictions on domain B. Thus, the learning was transferred from domain A to domain B. This transfer learning refers to this process of pre-training on a model on a large corpus of text data, and then will be used for fine-tuning it on a specific task. The knowledge and the linguistic patterns learned during this pre-training are transformed to the downstream tasks through the fine-tuning. This transfer of knowledge enables the model to perform well on various NLP tasks with a limited task-specific data. Right. Now let's start by understanding the architecture of transformers. Suppose we wanted to make a chatbot that can take these sentences and output the sentence. So for this, you will need an encoder-decoder architecture to perform, where an encoder will take the first sentence and encode it to some internal representation and pass those representation to the decoder to generate or predict the target sentences. And this is exactly how the transformer works. Let's break it down to understand the components. So the first step is to tokenize the sentence before feeding it to the encoder. Once it is done, then feed the tokenized vector to the embedding layer in the encoder part. The embedding layer will convert each token into a vector representation that will help the model to understand the relationship between the words, and then the output from embedding layer will get through the positional encoding. Now, what is this positional encoding? If you look at this input sentence, why transformers are better than LSTMs? Just exchange the positions of these two words, then the whole meaning of the sentence has been changed. But for the model, both the sentences are equal because the order of the word doesn't matter to it. That is where the recurrent neural network has the advantage of preserving the information about the sequence of words in a sentence, because they process each sequentially one by one. So, in order to preserve the sequential, we are using a clever technique called positional encoding. What it does is it adds a position vector into embedding vector, which holds the information about the position of each word. Let's see how it works. The researchers of this transformers uses the sine waves to compute the position vector by using this expression. Take a look at the sine wave, where the x-axis is the position of the word vector and y represents the amplitude of the wave. So, by putting the position of the current word here to get the position of the word at the y-axis. But the common problem that can rise here is two words having the same value of amplitude, which means those two words same, but we know that they are not same words. Here comes this part of the equation where it plots the sine wave for each dimension, which is I in the equation. So each dimension will generate a different sine wave, and that's how this problem is resolved. Now, if the two words is having same amplitude at this dimension, then we'll check in the another dimension, then for another dimension. The values will differ. And by taking the values of y-axis for each word, we will have our position vector, which will be added to our embedding vector to output final vector. So they used the sine and cosine waves for every even and odd position of the vector, and this is how the transformer retains the information about the order of words in a sentence without doing any sequential operations like R and N. This gives the parallelization advantage. Now this output will give most important part of the model architecture, which is the attention head. Now the attention head is for calculating how much each word is related to every other word in the sentence. But the attention takes three inputs: query, key, and value. Let's understand this part. This concept comes from the information retrieval system, where the query is a raw input, and after performing some pre-processing on the query, you will get the key and then use this key to match the best results in the database and the output the value using the key. And that's how the information is stored and retrieved. So the same scenario is here with a slight change, that is, input to the query, key, and value is the same sentence. So these three will be passed through linear layer, and the scaled dot product attention layer will calculate the correlation between words. Let's see further, zoom in and see how it is building the correlation. First, it will take the dot product between query and a key, which will output a correlation matrix where the values of each row and each column represents how much the word is in the row is related to the word in the column. This matrix is also called as attention filter. Then this matrix is the others divided these values into the values of this matrix by square root of the number of dimensions. In our case it is 6, to scale these values in a certain range. Then a softmax layer is applied in order to convert these values into probabilities. Now we have an attention filter that exactly represents how much a word is related to every other word in the sentence you have. Just have to take, now you have to take the dot product between this attention filter and the raw values of the original vector to get the most important features. But the researchers used multiple attention heads to capture more information, and that's the highlight of the paper. The output from multi-head attention have taken and concatenated them together, then pushed to a linear layer. That's how the scaled dot product of attention layer works. Then the output from this layer will get into add and norm layer, and what it does is that it takes the input from the attention layer and then previous input and then perform addition and normalization. And that's how the residual connections are also used in the network. Then the output will flow through the normal feed forward neural network with add and norm layer to the output to output the final encoded query and key. And hence this is the encoder part. Now let's shift our focus onto the decoder part. The first two layers of the decoder will be the same as the encoder, which takes the word and convert into embedding vector and then use the positional encoding to retain the information of the word order. So in order to generate the output sequence, first we feed the special token into the decoder in order to get it started. Then these two operations happen in the same way as it happened in the encoder part. Then the three copies of it as query, key, and value will be fed to the multi-head attention, and the output from this layer and then the previous layer will add and normalize using the add and norm layer. Now the next multi-head attention, the query and the key will be coming from the encoder and the value will be previous output, and this will build up understanding of current generated output and the previous query input, because the output has to generate according to the input. Then the output from this layer is again added to the output from the previous layer and normalized, and this will be fed to the input simple feed forward neural network with a residual connection and normalization. Then the final output from the encoder decoder will be passed through linear layer, which will output the vector containing the information about the next word. And to understand what's the next word could be just simply pass this output to softmax layer, which will output the probabilities for occurrence of each word. Then the word with the highest probability will be considered as the next word. These all operations are happened for a time step t equal to 0. And now in order to continuously predict the next word to complete the sentence, you just have to pass the current generated output to the decoder again, and it will go through the same operation and predict the next word. But here is a little problem. The attention layer in the decoder is there is an attention layer. The attention layer in the decoder build the attention filter because it has all the word known by it getting the input. But here in the decoder, you can see the next word is unknown to the network until it is predicted. So how does this layer build up the attention filter? The answer to this is it generates a new word. It assigns, as it generating the new word, it assigns attention weight to minus infinity to previous unknown words. And then at a final softmax layer, those all are numbers are get converted into the 0 probability. So for doing this, the researchers modified this attention head a little bit and added a new layer for masking, called this layer as masked attention head now. And the same way, the decoder will keep generating the output until it generates a special token which will represent the end of this process. And that's how the self-attention works, like a soul of the transformer. So there are 3 things to remember. One is, attention head takes query, key and value to compute the correlation between each word to every other word in the sentence to get the most important features to focus on. And the residual connections in the network give the advantage of flowing that stable gradients, especially in very large models, to avoid the problem of vanishing gradient. And the third is the self-attention give the capability to transformers to learn very long range dependencies. If you see, in 2018, 2 transformers were released that combined the self-attention with the transfer learning. One is GPT, Generative Pre-trained Transformer. This uses only the decoder part of the transformer architecture, which was pre-trained on the book corpus with the 7,000 unpublished applications. And another one is BERT, which is the bidirectional encoder representations from transformers, which uses the encoder part of the transformer architecture and masked language modeling, which is pre-trained on the book corpus and English Wikipedia. Transformers gave enhanced results with all the applications of NLP tasks. Text classification, text generation, text summarization, questioning, answering, language translation, and entity recognition. Let's move to the Google Colab notebook to explore how to build a spell checker in the Python. The spell checker is a software tool used to identify and correct misspellings in a text. This feature is commonly integrated into various services, including the word processors, email clients, search engines, electronic dictionaries, web browsers, messaging applications, and content management systems. By ensuring this correct spelling, spell checkers enhance the readability and professionalism of writing communications. First of all we need is to import the supporting packages. So pip install text block. We are installing the text block. From the text blob, now we imported the text blob class. Once it is imported, let's see, check the spell by correct method of the text blob object. So we created an object for the text block with the sentence, the birds are flying. I misspelled the word BARDS as the BORDS, and now we have to check the spelling by calling the correct method of the text block object TB just we had created. Then we got the corrected sentence. The words are flying. You don't know the word BIRD, so it gave the word WORDS. The words are flying, it is giving. So yeah, one more thing I made the misspell is filing. I gave it, but it's corrected the word flying. Instead of boards, it gave words. It didn't identify BIRDS. Okay, let's see. So in order to do that, we have to train the model on our own dataset, customized dataset. Now we can work on this type of errors. So for this, we build the custom spell checking AI algorithm, and let's see how to do that. For this, we will be installing the package called Speller with the pip install. Once it is installed, now, yes, it is installing. Then we have to build the spell checking algorithm. For this, we will import the package spell correction model from the speller model. For instance, this has been instantiated, and by passing the language English, we created the object SP. Now we need the data. Here I am using the sample data. It's not showing the right sample data was taken. So for this, I just created a sample data with the 6 sentences. The sun is shining brightly, the birds are flying, I want to play football, mountains are covered with the snow. Likewise with the 6 sentences, I'm going to train the model, just data being created. Now the model SP, whatever the object model, spell correction model SP, which has been created, been trained by passing this customized data. Yes, now the phoneme is created. Very good. Now I'm using this with the method spell underscore correct method with the object of the spell correction model SP, and by passing the misspelled sentence to this model, method. So the misspelled sentence, I prefer chocolate ice cream. These are the mistakes I made. When I run this code cell to do the corrections, the original text is I prefer chocolate, and the corrected word is I prefers. It gave I prefers chocolate, the spelling was corrected. Ice cream, the spelling was corrected. These 2 words were corrected. These 2 are the words which we are having here itself, chocolate chips and football. Let us try with the flying and football. Yes, here is the word birds are flying. Now I will try to give the words, this sentence to my algorithm to check how it is going to correct. Yes, the birds are flying. Yes, it's corrected. The birds are flying. It's flying is there. I'll take filing. And instead of word, I'll take boards. And I'm trying to check how it is going to correct. Yes, perfectly. The birds are flying. This is the spell corrected text. It's the original text. This is the spell corrected text. So you can try with different data. So to use the spell checker for your customized data set, This model has to be trained with your customized data, and then you can use for checking your data. Thus we can use this one. Here I explained, illustrated, demonstrated how the spell checker works using the text block. So many packages are also there, and we can see in the next lecture session we will see how to build a spell checker. Thank you.